Okay, I think we can start. Good afternoon, everyone. My name is Lilian Klug. I'm the scientific coordinator of POGO. Um, this is the eighth Nano webinar series. Um, so I see a lot of familiar names here, and hi to everyone I know. But I see also some names not so familiar. So let me introduce you to Nano first. NANO stands for NS POGO Alumni Network for Oceans, and it's a network of alumni or past scholars of the Nippon Foundation and POGO training initiatives in ocean observation. NANO's objective is to maximize benefits from training, facilitate the active contacts among the alumni and with their instructors, and promote joint research initiatives among these past scholars. One of these joint research initiatives is called NanoDope. It's a global project. NanoDope stands for a global study of coastal deoxygenation, ocean acidification, and productivity at selected sites. Objectives of the NanoDope is to, I'm sorry, my colleague in my home office. So NanoDope takes advantage of the dispersion of the alumni around the world, actually. And the project aims to promote in situ and remote sensing observations of the coastal ocean for this the oxygenation, ocean acidification, and productivity, providing opportunities for the project participants to strengthen their efforts to monitor essential ocean variables in their sites, and also organize activities where members can share experience. And the Nano Webinar series is one of these initiatives. So as I said, this is the eighth Nano Webinar, and all of them are recorded and posted later on our YouTube channel, on POGO YouTube channel. We advertise all of these in our social media. So this webinar will be presented by Dr. Anna Runyan-Seva. I hope I have pronounced this right, Anna.
Yes.
So Anna is one of the NS POGO Center of Excellence alumni. She's a senior data scientist at Hitachi Vantara, and she received a PhD degree from the University of Southampton and a bachelor and master's degree in physics from the Lomonosov Moscow State University. She is a member of NANO, of course. Her publications using Internet of Things technologies in marine robotic systems in studies of North Atlantic phytoplankton blooms were featured in Nature and were one of the top read papers in the Global Biogeochemical Cycles journal. At Hitachi Vantara, Anna is working on projects that use IoT and machine learning techniques to improve business operations across different industries. In 2017, Anna was shortlisted for Women in IT Excellence Awards in the Rising Star nomination. Well done, Anna. It's great to have you here. Thank you so much for accepting our invitation.
Thank you so much, Lika.
So we propose to have 30 minutes of your presentation, and then we open the floor for questions for another 30 minutes. But we're quite flexible, actually. For the audience, please be aware that this is being recorded. So if you don't want your voice or your face on YouTube later on, you can switch off those. And you can make your questions on the chat box. Thank you, and the floor is yours, Anna.
Thank you so much, Lika. And good afternoon, good morning, good evening, everyone. And it's my pleasure today to join this webinar series. And what I wanted to discuss today is the connection of machine learning and tech to tackling climate change. And I think it will be very interesting to discuss it with the community of oceanographers and climate scientists, how kind of these two areas can work together and how we can use machine learning tech to tackle some of the problems related to climate change. But before I jump into it, I wanted to tell you a bit more about myself. So this is how I look like. And I live and work in London, UK. And as like I said, I got my first degree in physics in Lomonosov Moscow State University. It's a very beautiful building in at the center of Moscow, Russia. And it was a great place to be a student. And after I completed my degree, I joined NF Pogo Center of Excellence in Observational Oceanography, and I spent a wonderful 10 months in Bermuda in 2011, studying observational oceanography and getting to know people from around the world and making friends for the lifetime. And after this program, I started my PhD in ocean neuroscience in the University of Southampton. So in my academic work, I was working with data from autonomous underwater vehicles, or you might know them as sea gliders. And these devices were deployed in temperate North Atlantic Ocean to track 1-year observations of chlorophyll concentration, temperature, salinity, and other key parameters. And the goal of this observation is to understand the impact of weather conditions like storms and surface temperature on seasonality of phytoplankton blooms. So we were trying to test different hypotheses for phytoplankton spring bloom initiation in the North Atlantic. And we also looking at the impact of individual weather events on phytoplankton growth, such as storms. So it was a very great project to be involved. And after completing my PhD, I got hired by Hitachi and to work as the data scientist, analyst, and specialist in sensor data. And in my current role, I work with data with a variety of systems, and we have projects in transportation, supply chain operations, telco, and other industries traditional for Hitachi. And you probably know Hitachi. It's a Japanese conglomerate, and it's a company of many companies. So the whole Hitachi ecosystem has around 900 companies, and my part of it, Hitachi Vantara, is a kind of the digital business unit within this ecosystem. But Hitachi does all sorts of things, from producing trains to building plants and building TV sets, building healthcare equipment, and also providing like a consultancy as well. So it's a very interesting company to work for. And an interesting thing that there is something that one of the devices that I was using during the PhD, it's the sea glider, and the modern Hitachi high-speed train have in common. And the thing that they have in common, that both of them represent the part of the Internet of Things. So the Internet of Things is, as I said, it's made up of devices, and from simple sensors to smartphone and wearables connected together. And these devices, they produce enormous amount of data. And this data can be used to build different machine learning applications to improve business operations. And you can see some numbers on the slide in terms of how much data they expected to generate. And it gives you a perspective of some of the complications of dealing with this amount of data to actually get something valuable out of it. And another thing that if you are working with the data from the Internet of Things, let's give, for example, a modern digital train, the high-speed train that has thousands of sensors, you cannot interpret by just visual inspection or traditional techniques from business intelligence and simple analytics. So let's say if I have one sensor and I'm receiving a time series data, I can make a plot, I don't know, in some of the dashboarding tools or MATLAB or Python, and I can visually inspect what is happening with the time series and try to determine potential interesting patterns. But what if you have the thousands of sensors? It's not possible for a human eye to inspect this multidimensional data and understand patterns from it. Therefore, you need to implement more advanced analytical techniques such as neural network or machine learning algorithms that are designed to deal with the multidimensional data, and with the right architecture, they can learn patterns and insights from it. So, as you probably know, that the field of data science and machine learning got momentum probably within the last 10, 15 years. And the question one might ask, why did it take us so long to start implementing this technique? And if you look at the timeline of development of these methods, basically we started a long time ago. Some of the first neural network research started in 1940s, and in 1950s there was the first kind of neural network that was built using 3,000 vacuum tubes, and it was simulating the functioning of 40 neurons. And basically, and even in 80s, we already had the backpropagation technique and multi-layer perception. So for instance, we had the right architecture to start training these networks. And we also started developing the first popular algorithms for machine learning, such as support vector machine. So I had a mathematical background that was developed over the decades. But one of the obstacles that was there to mass implementation of these techniques was related to the cost of storage, processing, and transmitting of data. So just to give you a perspective, let's say I have a project where I have my new digital train equipped with thousands of sensors, and I want to build a system that would predict potential failures of this train. I have my gigabytes of data, and let's say I live in 1990s, and I want to build a system. Just to give you a perspective, just to store this amount of data, hundreds of gigabytes, would cost me billions and billions of dollars. And nowadays, it costs you almost nothing. And if I want to start a computer and start processing this data, it will be beyond my lifetime. It would take so much time that probably even my grandchildren won't be able to achieve the results with the data processing based on the computational power that we have in 1990s. And it's also, if you remember, the internet in the 90s, the dial-in internet. And if you want to transmit this data from the train by this internet connection to the data center, it would take you 10,000 times slower compared to current 3G, 4G technologies. So basically, even if we had all this mathematical, expertise and techniques that could be applied for the data, we didn't have enough infrastructure to deal with the amount of data that is suitable for implementing these techniques. So we didn't have enough storage capability and compute capability, but the situation is very different these days, and we can start implementing this type of projects at scale. And also, this type of projects, there is the whole framework, how we can implement them. It's we start with the understanding of the problem, then we understand the data that we collect for this problem, then we run different steps for data preparation and processing, and then we develop our model, evaluate performance, and deploy this model to gain insights. So this is a framework that is widely implemented across different companies that do data science, data mining, machine learning. And it was established back in the 90s by the pioneers of the data mining market. And it's widely used today. So I gave an example of some of the machine learning applications, like I mentioned, predictive maintenance for the modern digital train. But the question that we might ask is, if these techniques are so popular and so so widely implemented today, how they can be used to tackle climate emergency. And we all know about erosion, ocean acidification, disappearing of Arctic ice sheets, and wildfires. So, and we also know that that tackling this issue cannot be delayed any longer. So we are already running out of time, and we need to see all the potential instruments that we can use to tackle this emergency, from prevention to mitigation and adaptation. And as you probably know, there's some of the IPCC report states that if we want to limit global warming to 1.5 degrees, and with this kind of limit, we can sustain a good amount of biodiversity and avoid some of the catastrophic events. We need to think about decarbonization and significantly decreasing our CO2 emissions, reaching net zero by 2050. And it involves many components, such as uptake of CO2 through some artificial methods, but such as carbon dioxide removal, decarbonization of industry, and actually transitioning to green and renewable energy sources. So, what does it mean for data science and machine learning? 1 year ago, a consortium of different universities had put together a research manuscript that describes implementation of machine learning techniques for tackling climate change across different sectors and industries. So, for instance, for the electricity systems, we can use these techniques to enable low carbon electricity. We can also prepare the infrastructure for kind of the different types of electricity sources, and we can use these techniques to reduce impact on the systems that we have. Also, for the transportation sector, we can use this technique to reduce activity and improve efficiency of the transportation, and also transition to, for instance, electrical vehicle, and make sure that we can do the shift efficiently and in the right way. For the industry, there is also a variety of applications, starting with the predictive maintenance. So, for instance, if we have a factory and we want to make sure that this factory is working in the most efficient way, and we are not producing extra emissions due to, I don't know, let's say the faulty equipment or the devices that are not produced in the right way. We want to build these predictive maintenance solutions to make sure that our equipment works in the most optimal way, and we keep the carbon footprint in check. And another important aspect is optimization of supply chain and making sure that we can track and remove some potential inefficiencies. And also there are a variety of applications for farms and forests, and tracking emissions, monitoring, doing precision agriculture, and potentially also predicting some events such as wildfires. And I'm going to talk through some of the examples of it in more detail. Let's say we are looking into building a predictive maintenance system, and we want to make sure that it works and we're collecting the right data that can be used for this problem. So this is an example how we can build some of the systems. If we have a machinery that has several sensors attached to it, we can collect this data and build what we call features to train machine learning algorithms. And typically we train these algorithms on the historical data, and this is just like an intuitive example that is provided on the slide. For each timestamps, we have different signal reading. We also blend this data with the maintenance records. So as another feature in our algorithm, we can introduce the times and sliced maintenance. And another example feature can be the workload on the system. And also, as our target variable, we have occurrence of failures that is represented in a binary form, such as 0, there is no failure, and 1, there is a failure. And what we would do, we accumulate this historical data, we train machine learning algorithms for predicting failures or remaining useful time. And as we start collecting new data, we apply trait model and generate predictions. So in this case, the maintenance team can be informed of the potential failures that can occur within an hour or like within 5 hours, or whatever timestamp you choose. And they can intervene on time and making sure that there is no factory downtime or the equipment doesn't produce faulty products. So in this case, we ensure efficiency. Another project that I want to tell you about is called Optimized Prime, and this is an example of implementation of machine learning in the transportation sector and in the electricity vertical as well. So this project is the largest trial of commercial electric vehicles in London, and it is driven by a consortium of several companies, including Hitachi, Uber, Centrica, Royal Mail, and UK Power Networks. So what is happening in this project? Basically, in a big cities like London, you want to transition to electrical vehicles to decarbonize transportation. And emissions from the transportation sector are around 20%, estimated as 20%. And the big cities like London can be one of the main emitters due to the high volume of transport happening in the city. But you cannot just transition to electrical vehicles overnight. There could be several complications with that. The first one is you might not have enough charging stations across the city. And the second one, if you start charging your electrical vehicles at home, you can have a significant impact on electricity grid, and it would be disturbing other processes that is happening. So in this project, there's experts in transportation, energy, and logistics. They got together, they shared the data, and they're using different algorithms and mathematical techniques to make sure that they can locate the charging stations efficiently across the city, and also they can determine the right pattern for charging of the electrical vehicles at home to making sure to minimize impact on the grid, on the network, and making sure that also the prices for the electricity consumers doesn't go through the roof. And also another implication of machine learning, another example of it, how it's more related to mitigation effects of the climate change. So for instance, you all knew that in California this year and previous years before, they experienced significant wildfires. And the effects were quite devastating and they were very widespread. And what would be helpful for places like California and other places experiencing these wildfires due to global warming is to make sure that we can predict the potential spots where the fires can occur and locate the fire brigades accordingly, or kind of alert the local population of potential danger of these events. So this is one of the projects that a research group at Stanford was running, and networks and the satellite data to built the model that would predict the live fuel moisture constant. And this is the proxy that they used to track potential hotspots, potential spots where the wildfires can occur, and mitigate them accordingly. So also, another interesting project related to this field, machine learning and data, was written by NOAA, and what they did, they used some of the data integration techniques, and they built a data warehouse to simplify access to the data for the community of researchers and business users and other users of the data. So they used some of the tools to integrate and standardize the data set and simplify the interface for the data accessing. And there's ensuring the data availability can also drive forward many research projects and help to achieve great outcomes. But it's also, we spoke about that how machine learning can be helpful and how the data is increasing and what are the potential applications for tackling climate change. But it's not, everything about it is not that great, because big data itself has its own carbon footprint, and it's estimated to be around 2% of the total carbon footprint that we have today. And it's even comparable to aviation. And why is it happening is to store this data, to run kind of all the things that we have on the internet, we need to build a data center. And on the slide, you can see a picture of the data center in North Virginia that is actually, I think it represents around 70% of the internet, the world's internet. And running this data centers, the electricity consumption by these data centers is huge. And just to put it into perspective, you probably all heard the song of Despacito that was very popular a couple of years ago. And I think it was streamed on YouTube around hundreds of million times, or maybe 1 billion or more. And the energy that's required to stream the song so many times was comparable to the energy consumption by entire countries in Africa, by some of them. So it just gives you a perspective of the energy consumption of the modern internet and of streaming and other services. So many of the tech companies, they got approached by Greenpeace, and they were asked to make sure that they keep their carbon footprint in check and make sure that they can run as much as possible on the renewable energy sources. And many of them do that, and they have the entire programs dedicated to it and have a strong commitment to go to net zero. And I think the Microsoft has a commitment to make sure that they can remove all the carbon emissions that they generated since the start of the company. But some of them are still in the transition. And some of the CEOs of the companies were asked by Greenpeace to make sure they can put planet before profit. And the reason is, with all the commitment to the renewable energy, some of them still rely on an energy supply like Dominion Energy that is not renewable, and there is still some contribution to carbon footprint. So the key takeaways from my talk, what I wanted to say, that the field of machine learning tech and is rapidly evolving, and there is so many interesting things are happening. There's so many techniques being developed, and the amount of data is growing every day, but we also have tools and mathematical techniques to deal with it efficiently. And there's also, we can think about multiple applications of this technique to tackle climate change and to help with this emergency, with the climate emergency. And I think it's also very important to have outreach events between machine learning and data science specialists and climate scientists and oceanographers to make sure that both roles are connected and can work together to tackle climate change. But we also, another important point that we need to make sure that we keep the whole IT industry in check and make sure that while we're all using it, it doesn't become another massive source of carbon emissions, and it becomes a solution as well as a problem. So thank you a lot for your attention, and I'm happy to answer any questions you might have.
Very good, Anna. Thank you very much. This is impressive, and I think that there is no way for us to go out as we keep producing more and more data. As you say, it's impossible for human eyes to, you know, assimilate everything. We will all have to recur to machine learning in the future, probably. I am opening for questions.
There's something in the chat.
So if you feel like having you have a question to Anya, you can switch on your camera and microphone and make the question live, or I can read it.
Well, I think there is a question from Krishna.
Yes.
Since machine learning continuously need improvement, is it the amount of data we have that determine the accuracy and efficiency, or there are other different factors involved? So typically, if you are training a machine learning model, there are several factors and that can determine accuracy of the model. It can be just the amount of the historical data, the type of features that you use to train the model, kind of the variety and relevance of them to the, let's say, variable that you are predicting. And it's another point is the techniques that you use, like machine learning algorithms, and how you tune them. So basically, let's say what type of algorithm you choose, what type of architecture of the neural network you choose, how you adjust parameters of them. So all of these factors combined can determine the accuracy of your model.
Mm-hmm.
Thank you. You're welcome.
Thank you. So while people are thinking on a question, I have one way before we start this talking. We were discussing this news from ESA that was published yesterday, that machine learning have been used to predict cholera, which is important health situation in India, but in other countries. And I was wondering, are you aware of experimental scientific advances in machine learning for predicting ocean-related impacts such as coral bleaching or harmful algal blooms?
That's a very good question. And I think like, I was talking about the big data, and from my perspective, the problem in oceanography that we still need to collect lots of data to describe the ocean, right? Mm-hmm. So we have a record of satellite data that is quite a decent data set, but it's still kind of, for us, for oceanographers, having more and more data would be more and more beneficial. So far I've seen some applications that are related to satellite data and image processing. And I think if you go on the website called kaggle.com, you could find some of the examples of, I think they were tracking some fish from image data. Mm-hmm. They were tracking whales, and also it was determined different types of phytoplankton from imagery. So yeah, it's the most applications that I've seen related to oceanography were related to image processing.
Mm-hmm. True. So we have another question from Acer. How to handle limitation of data in machine learning technique?
So it depends. What do you mean by limitation of data? So if there is not enough data to build an efficient machine learning model, you need to think about where you can collect additional data to make the data set suitable, and so your model is performant. And if your limitations involve something like missing data, you need to think about techniques how you can fill gaps in your data, gaps in your data, and make the data set more suitable.
Mhm. Is it? I'm remembering from my PhD thesis here. This was a solution for statistics, but I'm not sure for machine learning. Cross validation, is that a thing?
Yeah.
Yeah.
Oh, the cross validation is used here to check performance of models and tune hyperparameters. Yeah, that's it's widely used. Absolutely.
Mm. Okay. And while people are working on their questions, I have another one, and maybe this is a silly one because I really don't understand much about machine learning. But so one of the things that I've seen from your presentation is that the data is important and useful, but it's also something problematic on limited space of storage and things like that. So is it something that we can even use machine learning so to get rid of unnecessary data and releasing space? Or
That's a very good point. So, for instance, yes, if we are collecting that database of data, do we need to store everything, right? Considering the cost of running data centers and their contribution to carbon dioxide emission. And this is a very active debate, I think, in the big data community, is can we offload and start deleting some of the data? And the main question is how you determine which data to delete.
exactly, right? Because it may be not be useful now, but yeah, that's true.
So, for instance, like I was saying that I don't think like the data that is related to kind of online clicks, like visiting websites is useful. I don't see like any value for it, but people that work on positioning online advertisement, they would say, well, this is the data that I found the most useful, and I need to use this data to train machine learning algorithms to position online ads. And then I said, well, I think I personally find this online ads very annoying. But then I said, well, it's a modern way of advertising your business and technologies and like the products. So you need them to drive business. So it's very kind of difficult to say, well, this data is definitely useless.
That's true. An excuse to be a data hoarder. And so if everyone has a question, I'm dominating the discussion here. Sorry, please.
The question that I brought out to you, Lika, what do you think about what type of the outreach can be done for the tech community? So, because I think like there's lots of people that work for different kind of tech companies, and they're quite skilled in these techniques. But recently I had a podcast where I was talking about climate change, and it was actually absolutely astonishing how many people were not aware of the timescales and potential impacts. So I guess I would say running more outreach events would be very beneficial, because even people kind of work in this sector, they're not aware that, first of all, they can help with the issue, and second of all, they're not aware of the issue at all.
That's yeah, it's funny because like when we are, and you're the better person than me to answer this, because I'm still very much my networking is scientists and people that are aware of the issues, and That's a very good point, and I invite. We have so many experts here in the audience. Priscilla maybe can give a perspective as well. I think the only thing I can think right now, and while you were giving your presentation, I was thinking it's like this is a very strong point because we in Pogo advocate for sustained observational because it's like it's a paramount, super important that we have systematic uh, observation of the ocean because we do need a long time series, a regular time series, so we can learn processes, patterns, and learn what is natural from what's not, what's being um, forced from others. So this is a good. It's a very important. It's very important that these experts know um, that and help us advocate for this. I think that we have to make it more available. These kinds of talk that we have, for instance, our webinars here, and this is general. Learn how to talk to non-scientists because we keep using, specific terms and I think that we are going on the right way here. We see more and more outreach and scientists involved in outreach because it's now we cannot be closed in our little group anymore. We have to talk to people about it.
Yeah, absolutely, because it's sometimes I think the problem with outreach, especially related to climate change, is people don't like to hear bad news and they dismiss the information, or they kind of try to find counter arguments and to kind of distill the importance or the threat. So no, yeah, I totally agree if we can run more events together in the future and trying to reach out to people across different sectors.
That's a very good idea. I have one final question, which is more a curiosity. In one of your slides, you show the timeline for machine learning, and then it's between the 70s and the 80s. It's written dark age or artificial intelligence winter. What happened there?
Actually, yeah, I get this question a lot. Basically, there was a research publication, and in this publication, they also stated that we reached the limit of developing neural networks, and they described the reasons why there is no future for this technique, and we kind of hit like the bottom. And after that, this publication, the aftermath of this publication was significant reduction in funding for AI research, and it was lasting for almost a decade. And later on, it got the name AI winter.
Well, they were wrong.
Well, this is how kind of very opinionated paper can get you.
And Anya, does anyone else have a question? I was thinking here. So you're in a very different area, your career now, and do you see anything that you learned during your training at the Center of Excellence that turned out to be useful for you on your line of action now?
Yeah, absolutely. So basically, when I got hired for my position, what my future team told me is that you'd think in a very interesting way. And I think this way of thinking came from oceanography, where you need to connect physical oceanography, biological oceanography, chemical oceanography. And first of all, it shapes a very unique way of thinking, right? Because you connect all the things together to solve the problem. And all kind of, programming exercises, mathematical modules for very useful yes, I think it was. And another thing is networking and studying and doing projects with people from all over the world. So that was also very helpful.
Yeah, great. The multidisciplinarity, it's a fundamental indeed.
Yes.
All right, and Hannah, I don't think anyone else has questions.
Okay, well, if anything, my email is on the slide, and if any of the attendees has questions later on, feel free to reach out. And
yes, you can also contact Nano and me, and I can direct the question to Anna later. So this will be later available on YouTube, so you can watch it again and consider more questions or not. Anna, thank you so much for your time. It was a great presentation. I learned a lot from it. And I hope that we can work together and make all these IT geeks learn more about climate change.
Sure, absolutely.
Thank you so much and have a great weekend, everybody.
Thank you. Bye-bye.